Я имею честь представить вам Стивена Вольфрама. Давайте поприветствуем его. Ну, для тех, кто собрался здесь объяснять, кто Стивен Вольфрам, не надо. Поэтому я не буду долго говорить. А единственное, хочу поблагодарить Стивена Вольфрама, что он выбрал нашу площадку, наш вуз, местом встречи и также тем местом, откуда математика пойдет по всей стране. Предоставляю слово Григорию Фридману, организатору и вдохновителю будущих наших побед.
Спасибо большое. Добрый день или доброе утро. Приветствую всех, с кем знаком и с кем не знаком еще. Буквально два слова технических. Обратите, пожалуйста, внимание на программу конференции, которую вам выдавали. Она в 2 экземплярах. Надеюсь, вы все понимаете, что действует отдельный лист с программой, в котором чуть-чуть сдвинуты времена лекций. Вот это все, собственно, что я хотел сказать. И пожелаю нам всем удачной работы и слушаний. Все, спасибо.
Now you can hear me. Okay, it's great to be with you here today. I have visited this area once before in my life, but it was just pointed out to me that I've never actually been in Russia before because it wasn't Russia when I last visited. So I'm very pleased to be here and pleased to tell you a little bit about some of the technology that we have and that we've been working on and so on. So it's actually a very exciting time for us right now because a lot of things that we've worked on for a great many years are kind of coming to fruition all at once. Some of you may know that Mathematica, our flagship product, is about to be 25 years old. On June 23rd, it will be exactly 25 years since we first launched version 1 of Mathematica. And we've had a very long-term plan in building Mathematica, and I have to say that it's been exciting in recent times to see how successful that long-term plan is ending up being. And I think the products that we have are sort of stronger now than they have ever been. So we've been developing a series of versions of Mathematica. So, for example, late last year we brought out version 9, and this kind of gives some indication of the types of things that were added in version 9, things like social network analysis, being able to deal with units. I'll show some examples of some of these kinds of things, dealing with random processes of all kinds, some pretty interesting things probably for things like economic modeling and so on in that area, stochastic differential equations, things of that kind, reliability analysis, those kinds of things, in quite different areas, adding three-dimensional image processing. We've had very strong image processing in Mathematica. We've now added the ability to do direct image processing in 3D, and so on. And a whole variety of other kinds of things in signal processing and so on. Maybe I should start off by just showing you a rough indication of sort of modern Mathematica. So let me actually bring up Mathematica here and try and use it to do a few things. So let's start off. Maybe I have to make it a little bit bigger. Let's see, maybe that's big enough. Let's check that it's basically working. Okay, this is a good sign. So sort of the traditional way that one would use Mathematica is you say something like, plot sine x, and you get a plot. Or we could say, take this and choose to manipulate that plot, putting in a parameter a there, and then we say a runs from 1 to 5, for example, and now Mathematica will create this user interface that we can now manipulate for that plot. We could say, let's say something like this. We could say add another parameter here. We can make a 3D plot, for example. We can do the same kind of manipulation on the 3D plot, do all those kinds of things. And what's sort of important is how easy it is to start getting these kinds of things built in Mathematica. So So kind of, sort of the idea of Mathematica is that everything fits together in a coherent kind of way. So just like we can use manipulate to control, to manipulate pieces of graphics, so also if we wanted to, we could use manipulate to manipulate algebraic computations as well. So here we're just doing a different factorization every time we move the slider here. So kind of the idea of Mathematica, there's some principles on which Mathematica has been built, starting at the very beginning, more than 25 years ago now. One of the principles is to have a system that is as unified as possible. Kind of the idea in Mathematica is to do any kind of algorithmic computation, to be able to specify in the system and to build into the system any kind of algorithmic capability. Then one of the sort of principles of Mathematica is to have all the capabilities that exist in the system be as coherent and unified as possible, so that all these different kinds of capabilities all fit together. So the foundation of the system is this idea of symbolic computation, and we can take we could do something like this. We could say take some symbolic function f and iteratively nest it like this. We could say, for example, let's say the function we choose to nest is framed. Then we'll get something like this. Or we could we can take all kinds of the expressions that we're dealing with here can be any kind of thing. So, for instance, let's see if this works. I could say try and use the current image from this camera. Let's see if I can. Oh, there we go. Okay, there's a good current image. Okay, so now we can take that image and now we can do computations on that image. So, for example, we can say do edge detection on that image, and we'll get the result there. Or, for example, I could say something like, well, let's do something like this. Let's say, well, we could say something like dynamic of edge detect. Actually, I'll tell you what. Let me change this a little bit. Let's say dynamic of edge detect of current image. And now what I should be able to do, let's see. Yeah, there we go. Okay, so that's now doing edge detection dynamically on the image that we're capturing from the camera there. And you can take these images and do all kinds of things to them. Like, let's say we take that image and we decide, I don't know, let's say we make a partition of that image in little blocks of 10. So now we've got that image broken into little pieces like that. We could say something like, how about we say flatten that and then sort those I'll tell you what, no, let's make a tally of those little images, and what we'll find out, let's see, most of these images only occur once. Let's see if we sort by that. Let's sort these by the last element here, and now we'll find out, okay, so the image that's just pure black here occurs 319 times, an image that has a stripe like that occurs 5 times, and so on. And we could start, if we wanted to, doing all kinds of analysis and image processing and so on this. So this is sort of an example of how we can use kind of the underlying symbolic capabilities of Mathematica, but now apply them, in this particular case, to image processing. Let's take another example. Let's say we make something like this. We'll make just a mapping of this kind, and now we can take that and we can represent it as a graph. So now what Mathematica will do is to try and find a clear way to lay out that graph so that we can understand it easily. And again, we can do this. We could say something like make a graph out of this. Make there be n vertices in the graph. And now let's manipulate that with n varying from, let's say, 2 to 100 steps of 1. So now what will happen is we'll get, for every value of n, we'll get some graph laid out in sort of an optimal aesthetic way. So there are there are many, many things built into Mathematica. So, for instance, we can just look here at some of the capabilities of the system. In mathematics and algorithms, there's just a huge number of different kinds of things, whether we're dealing with mathematical functions or whether we're dealing with things in probability theory. There's some particularly nice capabilities that have been added to Mathematica in the last couple of versions to support symbolic probability measures. So just as a sort of random example of that, I can say something like X is distributed according to a normal distribution with mean mu, and standard deviation sigma. And now what I can say is, give me the expected value of, let's say, I don't know, x squared log x, with x distributed according to a normal distribution like that. Oops. What am I doing wrong? Maybe that's like this. Oh, dear. Well, when all else fails, look at the documentation. Okay, I did the right thing. What am I doing wrong here? Okay, somebody who's more expert than me should tell me what... oh, that's right. I'm old-fashioned. There we go. Okay, so this may be a difficult computation. I'm not sure. I just made up this computation. I'll tell you what. Let's make the computation a little easier, so we can get something to work here. So now I'm just saying find the expectation value here. I'm going to make this just so that we can make sure something works here. Let's make this really easy. Okay. There we go. Just to prove that this is a real demo. There's the result for that. So I don't know. I could say. So what I'm doing here is I'm just working out the expected value of this x squared times 1 plus x, with x distributed according to a normal distribution there. So it's just one example of a zillion different things that we can do in Mathematica. So if we look at over the course of time, sort of an interesting plot, we can kind of get some idea of what's been in Mathematica by just plotting as a function of time over the last 25 years the number of built-in functions in Mathematica. And what you see is that for a long time we kind of tried to keep the number of built-in functions kind of limited, but then in the mid-2000s we just decided we've got a very good framework now. Let's just try and implement sort of all possible algorithmic functionality, and that's the path that we've been on for the last more than 10 years now. And what's been very interesting is that we're able to implement new functionality at an increasing rate. This plot is sort of misleading because each individual function that we add now tends to be more of a superfunction than an individual function, a function that's capable of doing many different things. So one of the things that's been important to us is having a system where all the pieces fit together has allowed us to build at an ever increasing rate. See, one feature of modern algorithms is that it's typical that in an algorithm for doing, let's say, numerical computation, one actually will need to make use of algebraic calculations or graph theory or computational geometry, all these different areas. So even though you think you're doing numerical computation, actually to have the best algorithm, you need to make use of completely different areas of algorithmic functionality. And for us now, because we have all these areas of algorithmic functionality, functionality, it becomes easy for us to develop kind of more powerful algorithms. Another thing that's been important to us is one of the sort of principles that we followed in developing Mathematica is the idea of automating as much as possible. So kind of my notion in building Mathematica is sort of the human gets to say what the goal of a computation is, then the system should automate as much as possible how to get that computation done. So, for example, when one has, let's say one's finding the solution to a differential equation, what one will tell the system is just find the solution to this differential equation. But then there might be 300 different algorithms that the system knows for finding solutions to differential equations. But then what it does is to automatically decide between all those algorithms to work out which is the best one to use for the particular equation that you've given. And increasingly what we are doing in building Mathematica is developing not just algorithms, but meta-algorithms, algorithms that kind of control between many different individual algorithms. And one of the things that's been important to us, we've been sort of filling out a lot of algorithmic capabilities, some with algorithms that are already known, but increasingly with algorithms that we've invented for particular purposes. Well, originally, I personally, one of my motivations for developing Mathematica was to use it to do scientific investigations myself. And I might mention a few of those pieces of science that I did that, in fact, now have fed back into the development of Mathematica and our other products. So, about 10 years ago now, I published a big book called A New Kind of Science. That was the result of about 20 years of research that I'd done. And kind of the idea of this book was that I was interested in generalizing the methodology that's been used for exact science for the last 300 or so years. That methodology has tended to come from sort of the Newtonian kind of paradigm, where one wants to find mathematical equations to describe features of the natural world. What I got interested in was how do we generalize that? How do we use sort of arbitrary sets of rules for describing the natural world, not just equations? And so I got particularly interested in some systems called cellular automata. Here's an example of one. It's a very simple program that just starts off with, just has a line of cells, each one either black or white, and it just evolves in a series of steps. And there's sort of a summary of the program at the bottom and then the behavior of the system. And what I got interested in was if we're going to describe the natural world, for example, with programs, what kinds of programs might these be? They're probably not programs that are thousands or millions of lines long that we're used to writing to perform particular tasks. They're probably very simple programs. And so I got interested in the kind of basic science question of what do simple programs typically do. And so some programs that you find that you can look at just do very simple things. Here's one that does something slightly more elaborate. If you continue it for a while, it'll make a nice nested pattern, but it's still a very regular pattern in many ways. What I got interested in was what do all possible programs like this, how do they behave? And actually, we can easily do an experiment now in Mathematica to study that question. So let me just do an example here. So let's say this is I can work out one of these cellular automata. That's the one I just showed. Maybe I can work it out for more steps. Let's go for 500 steps. There it is. But now let's try the following. Let's try saying, let's look not just at the specific cellular automaton, but let's make a table of all cellular automata. Let's see. Let's make a table of, let's say, the first 64 cellular automata with rules of the type that I was showing before. And here's the result from that. And we see that most of these cellular automata do very simple things. They just start off from one black cell and just make little stripes or something. But eventually we get to this one, rule 30, and it does something more interesting. So let's try running that a little while longer here. Let's just take this, and we can just do this experiment in real time here, and take Rule 30 and run it. Let's run it for 400 steps, and see what it does. So there's the result. Let's try making that a little bigger here. So this is really a very, very bizarre and remarkable thing. I mean, we can see there's a certain amount of regularity over on the left, but for many purposes, this pattern looks completely random. Even though we can summarize, for example, here, there's that rule at the bottom is the rule that specifies this whole pattern. Yet the pattern, once it's generated, looks for many practical purposes completely random. Well, in fact, we know it's really quite random because, for example, the center column of this pattern we've used as a pseudo-random number generator in Mathematica for a long time, and it's passed sort of every test of randomness that anybody's been able to throw at it. Well, so in the direction of science, I've been interested in how simple rules what happens with simple rules in this sort of computational universe of possible programs. And I found all kinds of things. And this is a Turing machine. You can find that you don't have to go very far in the space of all possible Turing machines before you again get very complicated behavior happening and so on. This is a very general phenomenon, and it's a phenomenon that's also relevant for understanding what happens in the natural world. So, for example, here's a snowflake. Turns out that there's a simple model that's based on one of these cellular automata that captures very well the overall features of the behavior of something like a snowflake. And you can find these phenomena all over the place in biology and other places. And what's been interesting to me is that when you want to find a new model of some phenomenon, one approach that you can take is try and find a mathematical equation to model that phenomenon. Another approach that you can take is try and find a simple program to model that phenomenon. And in the last 10 years or so, I think it's been the case that there's been a rapid increase in the use of simple programs as models for systems. And actually, I think if you look at the new models that have been produced in the last 5 years or so for all kinds of different systems, whether they're human systems, social systems, economic systems, even physical systems, more of those models have been produced with simple programs than with mathematical equations. So this methodology is really winning out. But there's another thing that's important about this, which is that when you see these simple programs doing very complicated things, you might start to think, if we want to do a particular computation, could we perhaps just search the computational universe of simple programs to find one that does the computation we want? And it turns out that there's this thing I call the principle of computational equivalence, which is a general principle about how sort of computation works in this computational universe. One of its predictions is that among these simple programs, as soon as they show non-trivial behavior, they will, for example, typically be universal computers. So, for example, this cellular automaton, it's rule 110, we know that this one is a universal computer. We might think that to get something as sophisticated as a universal computer, we'd have to build some CPU with lots and lots of gates and other kinds of things. But actually, just that simple rule at the bottom of the screen there is enough to give us universal computation. Well, so that's interesting, and we can do other kinds of things. We can start sort of searching the space of possible systems for interesting cases. Here's an example in mathematics. This is sort of a complete. This is kind of the axioms of mathematics as mathematics is usually practiced, just sort of all written out on one page. We can ask ourselves, why do we use these axioms and not others? And we can just, for example, enumerate possible axiom systems for mathematics. We do that down the left here. Across the top is possible theorems, and then there's a dot every time a particular theorem is true for a particular axiom system. So in effect, every row of this picture is like a field of mathematics, and we're looking at the different theorems that occur in that field of mathematics. And nowadays, this was a picture that I made for my book some time ago. Nowadays, you can make this picture using the full simplify function in Mathematica, which includes a very powerful equational logic theorem prover for proving these kinds of theorems. But the question is, in this sort of space of all possible mathematics, where does the mathematics that we practice lie? So as an example of that, we can, for example, look at something like Boolean algebra and ask, how far out in the space of possible axiom systems are the axioms of Boolean algebra? The usual one's pretty complicated, but what I found is that actually this axiom here is a complete representation of Boolean algebra, and it's the simplest representation that one can find that exists for Boolean algebra. And it's about the 50,000th axiom system that you get if you just enumerate axiom systems in kind of order of complexity. So this kind of suggests that if we just search a space of systems, we'll find things that are interesting and useful. And in fact, nowadays, when we try to find new algorithms for things, a very common approach that we use is just this idea of algorithm discovery, of searching the computational universe of possible programs to find ones that perform particular operations that we want. So that's kind of a new methodology for finding algorithms, different from the traditional one of sort of engineering the algorithm step by step. Well, okay, so one of the big pillars of our sort of technology world is Mathematica. Another big pillar of our technology world is Wolfram Alpha. Wolfram Alpha is a system with a very ambitious objective. The idea is to make a knowledge engine which can make as much of the world's knowledge as possible computable. So what I mean by that is, let's say we ask it a question. Let's say, what is the integral of x squared cosine squared x? Now, it will give us the answer. It will also start to tell us other things that it thinks we might find interesting, given that was the question we were asking. Like, there are some definite integrals that are related to that. There are some plots and so on. For students around the world, we've provided this capability for being able to take that integral and show steps that you could use as a human to do that integration. I should say that these steps are, in a sense, completely fake, because the actual way that Wolfram Alpha and Mathematica underneath do the computation is something quite different from these steps. It uses very powerful algorithms and theorems and so on to get results. This is just a simplified version built purely for the sake of humans. So we can ask Wolfram Alpha all kinds of things, like we could say, I don't know, we could feed it some differential equation. We can write it in any kind of horrible notation, and it will go and try and figure out what we meant and give us solutions to that differential equation and so on. Each of the things that we're doing here has a representation inside Mathematica, and we can do these individual computations in Mathematica. Wolfram Alpha also knows about lots of kinds of knowledge. So in addition to things like mathematical knowledge, I can say, something like, what is the density of gold? We were just discussing, what just happened here? Hopefully we can get connected to the network. Yeah, there we go. Okay, so now it'll tell us there's the density of gold and so on. So now let me try asking something. We were discussing this building that we're in right now, which used to be a central bank, and apparently gold reserves were stored here. So I have to ask, how much does $1 billion worth of gold weigh? Let's see if we can answer that question. I'm not quite sure if we'll be able to answer that question. Let's give it a try. Oh, there we go. So convert $1 billion of gold. Okay, so it weighs okay, so it's about so it weighs about 22 tons. So the floor must have been reinforced in this building, I think, to support all the gold reserves. But here we're making use of kind of real world knowledge and doing computations with it. So, for example, we can say, we could ask about the GDP of Russia, or we could say that's a nice increase there. We could say what's the what's the okay? So there it is in different sectors and so on. We could say GDP of Russia divided by Italy, let's say, and see what that looks like as a function of time for the last few years. Or we could say, we could ask something like, I don't know, we could say Microsoft versus Apple, and this will now consider these companies and now give us data about, okay, there it is, from, I guess the markets are closed right now, so this is data from when the markets were last open, so that's showing us comparative price histories and all those kinds of things. So all of this stuff, or we could ask something about St. Petersburg. We could just say, tell us what you know about St. Petersburg. It'll tell us things about the population and location and so on of St. Petersburg. Or we could say, okay, we could say St. Petersburg weather. This is always fun because you have this whole giant stack of technology, and then you can look out of the window and find out whether it's correct. It looks promising. It says it's sunny, and it is sunny outside. And we could, if we want to, there's a plot, for example, of the temperature as a function of time for the last few days in St. Petersburg, and there's the projection for the next few days. We could show, for example, us the temperature as a function of time for the last 10 years. Wow. It's, okay, so this says it got as cold as minus 30 degrees centigrade here, and as warm as 37 degrees centigrade, and at different times in the last 10 years. So the idea of Wolfram Alpha is to be able to get sort of knowledge about all different kinds of things. So if I type in something like this, Wolfram Alpha will assume that that's a genome sequence, and now it'll find matches to that genome sequence on the human genome, and so on. So there are all kinds of different areas of knowledge that Wolfram Alpha deals with. It's a very large system, and it's kind of has several parts. I mean, one part is kind of getting the raw data, and this is data that we have got from primary sources. We wouldn't be able to get this kind of data from the web. There's much too much data that we now have. The raw data that we have is actually bigger than the text content of the whole web. But also the data that exists on the web is not systematic enough. So we have to go to primary sources of data to get them, and we have data on just a very large number of different kinds of things. So that's sort of the first step. The second step is that typically you don't just want pure data. You actually want to do computations from that data. And so the second thing that we've done is to implement a large number of different algorithms that implement all the sort of methods and models and so on that exist in different areas of science and engineering and such like. So, for example, this is the International Space Station, and we know from a feed of data that we have from NORAD in the US. We know from radar measurements where the space station was. In this particular case, 9.7 hours ago. But then we have to actually solve the equations of celestial mechanics to work out where the space station is now. And so, for example, here it will tell us where the space station is, and it knows that I'm in St. Petersburg. So it says that the space station is not currently visible from St. Petersburg, and it will next rise at this time, and so on. So another feature of Wolfram Alpha is this ability to understand natural language, that we can ask it some question like, how fast is the ISS going now? And it will be able to understand, I hope, that question and give us an answer. And in fact, this capability of understanding natural language is used when Wolfram Alpha is deployed in lots of places. This is used. So, for example, in the Siri intelligent assistant on the iPhone, you can ask it questions, and it's using Wolfram Alpha to give. You can ask it questions by voice, and it's using Wolfram Alpha to give answers to those questions. We can also use Wolfram Alpha's linguistic capabilities in Mathematica itself. So we could say something like, plot a sine curve, and now this will actually use Wolfram Alpha's linguistics to work out the Mathematica code. It will synthesize this piece of Mathematica code for plotting a sine curve. Or we could say something like, add a purple frame. And now it'll again go to Wolfram Alpha to get a piece of code synthesized that will do that. Or we could say, blur the image by 10 pixels. Let's see if that works. It might understand what I was talking about. There we go. And it did image processing now on that image. And again, it's synthesizing code just using Wolfram Alpha. Now, another thing you'll notice down here, this is a new feature in the latest version of Mathematica. It's a prediction bar, suggestions bar, that predicts what you might want to do next. So, for example, here it says, okay, this is an image. Let's see, maybe we want to use a filter here. Let's try using a commonest filter on that image. Okay, it allows us to change the radius here. Not quite sure what that filter does, but there it is. And so what this is doing, whenever we do a computation now, for example, let's say that we do a simple computation. Let's say we type in, 1 over x cubed minus 1 or something. Now it will say, what do we want to do? Do we want to plot it? Do we want the denominator? Do we want the x derivative? Let's find the x derivative of that. Let's go ahead and find the limit of that as x goes to 1. Maybe we can go back here and say, okay, let's plot that instead. There's a plot. And in each case, it's making a prediction for what we might want to do next. And essentially what it's doing to make these predictions is it's running a lot of computations, and it's figuring out which of those computations might give an interesting result, and then it's suggesting those as computations to do. It's also using the many billion queries that have actually been done in Wolfram Alpha by people around the world, and using the statistics of those queries to work out a priori probabilities for what people might want to compute. So that's an example of how sort of Wolfram Alpha is integrating into Mathematica. Another thing we might do is something like this. We could say we could get data from this is sort of Wolfram Alpha data in Mathematica, and now we could, for example, say I don't know. Let's get the shapes of all those countries. There we go. Or maybe we can try here. Here's a fun thing to try. Let's try finding the flags of the countries of all those countries, and then maybe we can do image processing on those flags. So, for example, we could try doing. If we finally get the flags here, let's see. Oh, there we go. There are all the flags, and now we could, for example, try doing edge detection. So now we can, that will do edge detection on each of those flags and so on, and we could start doing analysis on these and so on. So it's very significant that we can get this data directly into Mathematica to be able to compute with. And actually in future versions of Mathematica, pretty much all of the data that we've accumulated in Wolfram Alpha will be very directly accessible in Mathematica. I should say... So I mean, we have a number of sort of core pieces of technology. One thing that is a core feature of Mathematica is the language on which Mathematica is based. This kind of symbolic language that represents all of these different computations. And we're now calling that language the Wolfram language. It's kind of the core of most of our technology. And kind of the idea of the Wolfram language is a little different than the idea of basically every other programming language that exists. Because most programming languages try to maintain the simplest possible core of computational operations and then expect you to kind of build up everything from there. And maybe there are libraries provided for particular purposes, but it's all kind of a somewhat ad hoc thing. the idea in the Wolfram language is to just include as much algorithmic functionality as possible directly inside the language. So all these different kinds of capabilities all are part of the language, whether you want to make some piece of graphics in 3D, whether you want to analyze some network, whether you want to do some optimization problem, all these things are just part of the language. Whether you want to import data from all sorts of different formats, all of these things are just part of the language. So that's an important direction that we're going, is this Wolfram language that is sort of a core of many different products. So another thing that is CDF, our computable document format, and kind of the idea of CDF is to provide a way to create interactive documents extremely easily. So, for example, we have a demonstrations project that has about 9,000 or something of these demonstrations that cover lots of different areas. I don't know, let's pick an area. How about, let's do business. How about economics? Let's see what there is in economics. So let's look at some of these. Okay, so for example, let's try doing, I don't know, present value of future gas use. I'm just going to pick this at random. These are things contributed by different users. And so what this is now an interactive, so I'm just playing around. I don't really know what this is. This is probably some predicted curve. And now we're able to interactively compute things right here in our web browser. And for example, we might say, let's say, well, this is the code. This is the Wolfram language code that underlies this CDF document. Okay, so CDF is another sort of core part of our technology stack. It provides the ability to have interactive documents that right now can be deployed either on the desktop or in a web browser. Also, very soon it will be possible to deploy them on mobile devices and so on as well. Another piece of our core technology stack that's coming in the future is the thing we call WDF, the Wolfram Data Format. And the idea of that is one gets data about all kinds of things, and the question is, how should one represent that data? And let me show you something that exists in Wolfram Alpha. Wolfram Alpha lets you upload data as well as using sort of public data that exists in the world. So, for instance, we could upload some data here, and this will just be data that comes from a spreadsheet or something like that. And what Wolfram Alpha will then try to do is to figure out as much as it can from that data. So this data was just raw things of two letters and a number with a $sign. But then Wolfram Alpha figured out that it should make some plots here, and it should try and do some statistical analysis, regression analysis, and so on, try and find distribution functions and so on, try and make essentially statistical conclusions from that data. Well, one of the things that one can then do is to take data and try to understand what the semantic content of that data is, what the rows and columns mean, and so on. In Wolfram Alpha, we have sort of for the first time this real capability to do understanding from natural language of things, so that we can take kind of all sorts of data, whether it's data about chemicals or species or financial data, and understand what kind of data each of those pieces is. And so in this WDF, Wolfram Data Format, what we'll be doing is to let one linguistically analyze all sorts of data and turn it into a standard form capable of further computation. Well, another piece of our technology stack is something in a quite different direction. It's a product called System Modeler. And let me see if I can show you an example here. Here we go. So System Modeler is something for doing large-scale systems engineering, for building engineering systems that have, let's say, 50,000 or 100,000 components, whether it's an aeroplane or a ship, or perhaps even an economic system that has a large number of components that interact with each other and that are described by equations. And what System Modeler does is to give you kind of a visual way to create sort of the network that represents the operation of that system and large collections of different component parts in a standard language called Modelica, which is increasingly being used by engineering companies who build components to specify how their components work. And then what System Modeler allows you to do is to analyze, to set up those equations, solve the equations, make an analysis of the behavior of the system, simulate what the system will do. And this is all connected together with Mathematica so that you can take this large system and analyze it in Mathematica also. Well, so we're working very energetically on we released version 9 of Mathematica late last year. We're working very energetically on the next version of Mathematica, and it will have many, many new capabilities. It's interesting that there are areas of Mathematica functionality that really we've been building towards for a decade or more, where we just have to do a series of many different layers to be able to get to the point where we can really add these capabilities. But we've got some very interesting ones that are coming in the next version of Mathematica. But I think one of the things that will probably define the next 6 months or a year for us, beyond adding all these capabilities to Mathematica, all sorts of new capabilities to Wolfram Alpha, the thing more than anything that will define what we're doing is new ways to deploy the capabilities that we have in the Wolfram language and CDF and so on. So let me show you one thing that's coming soon. This is called Mathematica Online. This is a version of Mathematica that is running completely in the cloud. So this is just a regular web browser, and now what I've got here is all these Mathematica operations, hopefully, if it works, that are running completely in the cloud. So I can just say, this is just a web browser. I could say, make a 3D graphic here. It loads up, and now we can rotate it around. But this is all just a web browser. We can even do some. We could even, for example, say something like manipulate. What can we do here? Let's say plot. Let's do something boring. Let's do a standard kind of thing. Let's do something like this. And now we can when we manipulate this, we should. Hopefully, it will work here. Okay. And so now here, this is again just a web browser. So every time I move the slider, it has to go out to the cloud to get a result. But that means that you can create interactive content that you can just embed in a website, and all of the computation happens in the cloud. So this is there's a lot of different aspects to this ability to run the Wolfram language in the cloud. So, for instance, one of the things that this is sort of a general cloud platform, and one of the things we're going to have is a thing we call the programming cloud, which is something where basically you create a program in the Wolfram language, and then you get to deploy it in all sorts of different ways. So you might deploy it by having an active website. You can also just press a button to create what we call an instant API. So let's say you've built some functionality in the Wolfram language. Let's say it does image processing or something like this. You can just press a button and instantly get an API that you can call that will do those image processing operations for you. So you just get a URL that you can feed data to, and then that URL will cause a computation to happen in our cloud and get results sent back to you. So this is kind of a way to incorporate Wolfram language functionality into any kind of application, and there'll be ways to integrate that API not only into websites but also into programs in any other language and so on. Another automated capability is report generation. And so what will be possible here is, in a very streamlined way, to create kind of reports that you generate on a particular, so there might be underlying data that you're looking for, and then you can go and you create one of these CDF documents, and in it you have live data. And this is showing, this particular data is showing my email over the last, let's see what's happened. Okay, that's not too bad. I've obviously been keeping up as I'm traveling around. I've obviously been more or less keeping up on my email here. But this is pulling data from a real-time database, and then using our cloud platform stack, putting data out into the cloud, and then displaying it, in this case, within the framework of Mathematica Online, but it could as well just be an independent website. So kind of the idea of this programming cloud and all of these kinds of things is to be able to let people, if they want to implement algorithmic functionality, to give them a very streamlined way to do that, to use the Wolfram language with everything that's built into it, to create programs that can then be deployed immediately on the web and anywhere you want. Actually, another kind of deployment is to deploy them on mobile devices, and you'll be able to deploy them either using the cloud as the backup computation system, or actually deploy them to run interactively on the mobile device. So the first thing that will come out is CDF for iOS, and that will allow you to build apps that are based on CDF natively under iOS. So there are many different directions, many things that will come from this. There's kind of a general document platform that we're building using CDF and using the Wolfram language. One application for that is building online courses, and so we actually have a very elaborate a framework and system that we've built for authoring and creating online courses. And these are kind of pretty interesting online courses because they use the Wolfram language to let people at every moment get interactive access to try experiments for themselves on what's being discussed in the course. And I've been actually myself building a data science course as a prototype of what can be done with our course authoring system and with CDF and the Wolfram language and so on. Well, another feature of what we're doing is we're doing a lot of stuff with data, and we're building a general data platform that lets one analyze all kinds of data. And actually, just as some examples of kinds of data that we've been involved with. So, for instance, well, I've been a data enthusiast for a long time. So for example, that's a plot of my email for the last 23 or so years, showing a dot for every piece of email that I sent as a function of time of day and so on. So you can see that I've been, times when I was asleep and awake and so on, and times when I was taking trips to Europe and things like that because the times are shifted and so on. And you can work out, it's just sort of a fun example of using data that's kind of, my personal daily rhythm of keystrokes and emails and meetings and steps taken and so on. One of the things that we're doing, there are a large number of different kinds of devices that are coming on the market right now for measuring all sorts of different kinds of things. There's sort of an explosion in hardware, small hardware apps, hardware devices, and we're building a general connections hub that will provide sort of a general analytics layer for anybody who has one of these kinds of devices, so that all of this data from these devices can flow into our technology, whether it's the Wolfram language, Mathematica, Wolfram Alpha, and so on, and be able to get access to all that data. Well, there's lots of data out there in the world. I'll show you an example of something we did recently. In Wolfram Alpha, you can connect Wolfram Alpha to your Facebook profile, and it will then automatically try and give you all kinds of analysis of your sort of life on Facebook. And the way that this My particular Facebook profile isn't terribly interesting, but there's kind of a small version of lots of the sort of little book that Wolfram Alpha can produce using underlying Wolfram language technology to about sort of my life on Facebook. But anyway, the result of providing these capabilities is that a lot of people use them, and we got a lot of kind of anonymized data about people's habits on Facebook. And so just as an example of sort of what one can do with data analytics using Mathematica and so on, this was about 3 person weeks of work to do lots of analysis of a very large number of Facebook profiles. So, for example, this shows how many friends people have as a function of age and gender. Red is female, male, blue is male, and it shows that teenage, somewhat unexpectedly to me, teenage boys have more friends on Facebook on average than teenage girls, for what it's worth. And we can look at all sorts of different things. Like this is this shows, as a function of the age of a person, it shows the distribution of the ages of their friends on Facebook and so on. Or we can look at something like what fraction of people are single and married and so on, according to what they say in Facebook. Or we can look at something like how do people migrate between countries. Actually, here's another thing. We can look at the median number of friends that people have on Facebook, and I think probably Russia is low because probably Facebook is not the dominant social network used in Russia, and Iceland is high because everybody's related to everybody in Iceland. But this shows us we can also look at things like migration between countries based on where people say they're from in Facebook and where people say they're living now in Facebook, and so we can see, migration was Russia. There's some migration to the US. There's some migration to Germany, and so on that one sees in this plot. And it's interesting, the kinds of data that we can work with using the Wolfram language. There are all sorts of different kinds of data. So another kind of data, actually, this will be coming in the future version of Mathematica in a more prepackaged way, is being able to look at natural language, textual data. And so this, for example, is looking at a corpus of Facebook data and asking the question, as a function of people's age, what topics are they interested in? So it shows, people get less interested in video games as they get older and more interested in the weather as they get older. Those kinds of fun things. So, in any case, these are just some examples of applying the Wolfram language and our technology stack to different kinds of things. There are lots of different applications. Another new direction is embedded computation. So, over the last 25 years, Mathematica has run on pretty much every kind of computer that it's realistic to have it run on. But when you have a device, a small consumer electronics device, the computers that are in those devices haven't been powerful enough to run Mathematica until now. Basically, this year is the turning point for that. And so, for example, on the Raspberry Pi computer, which is this little $25 Linux computer, there'll be a native version of Mathematica that can run on that. And so you'll be able to take an algorithm, a computation that you've specified, perhaps using the programming cloud, and immediately create a standalone version of that can run natively on this little embedded device. And so that means that you can actually run Mathematica inside a consumer electronics device, and use it to do image processing or whatever else you want. So that's kind of one end of the spectrum. Another end of the spectrum is Mathematica has for several years supported very simple-to-use parallel computation capabilities. Those will be greatly expanded as it becomes possible to make use of very large external clouds running Mathematica. So, there are lots of different things that have been kind of made possible by kind of these underlying technologies, the Wolfram language, CDF, our large knowledge base in Wolfram Alpha, our large algorithm base in Mathematica. All these things have kind of come together to allow us a lot of freedom in in the kinds of products that we can build. And I think there are some really exciting opportunities for people, because I think just in the next year, one will be able to take kind of knowledge of Mathematica and the Wolfram language and so on, and use that knowledge to build a large number of different products and to sort of deploy algorithms in lots of different areas. There are also all these new opportunities in building courses and things, making use of our platforms and our technology and so on. A lot of different opportunities that exist. And I think I've been excited that we set down certain principles for building our technology and our systems more than 25 years ago now, and it's sort of exciting to see that that we've really that those principles have really worked out, and that now we have a very strong system moving forward that we can use to create a lot of important functionality. Well, I should probably stop there, and I'd be happy to have questions, comments, discussion. So, thank you very much. So, please. Questions? Yes, please.
Stephen, could you ask Wolfram Alpha under which conditions 2 times 2 will be equal to 5?
Under what? Under what?
2 times 2 will be equal to 5.
We can try. I don't know how you would ask that. We could say something like, when is 2 times 2 equal to 5? I think it's going to say it doesn't understand what we're talking about. Okay, it says 2 times 2 equals 5 is false. That's probably a good start. It's not going to get confused and explode or anything. Yes.
What about Rvachov functions in Wolfram Alpha?
Rational functions?
Rvachov R functions.
Sorry, say again.
Yes,
what
yes.
kind of functions?
Yes.
Maybe say it in Russian and somebody will translate it.
Скажите, пожалуйста, о R-функциях в системе Wolfram Alpha. Функции Рвачева.
So, if you're asking about the R statistical language, or you're asking about no R. So I don't know what. I'm not sure. Is this a type of special function or? Yes. I thought I knew about all kinds of special functions. I don't. Let's. How about let's look at this. So.
Is Mathematica for Android on the horizon anywhere?
Let me try and answer this question about then I'll so let me just try to understand what you're talking about. So you're talking about some type of special function like this kind of thing. So what are functions? Are functions? I'm going to resort to. Let's do something. Let's ask the web, and then I might be able to know what that means. I don't know what you mean by R functions. I'm sorry. Anybody?
I think it was some particular kind of special function with some name, whatever.
Okay. Okay. I don't know. No, so, wait a minute. Impossible. Oh, okay. Well, yeah, so I mean, what can I say? It seems that this is something to do with things like logical operations. So, for example, we could say something like, not Q or something. Let's feed that in just as an example of something. Let's feed this in to Wolfram Alpha, this is just some logic operation. That wasn't actually. This was a logic operation which turned out to be trivial, where everything is true. Let's see what happens. That's also trivial. Never mind. So I'm not able to answer this question because I don't know. Maybe afterwards you can explain to me what. Yeah. One more time.
Это обычные действительные функции, просто их знак зависит от знака аргумента функции. То есть это не специальные функции.
Okay.
Спасибо.
I would think that you could easily program such a thing, but it's not a built-in. I mean, I don't know how to. There's no built-in capability for the thing. If I understood correctly what you said, but that's. The whole point of Mathematica is that it's programmable, and so kind of the concept is that you should be able to program it to deal with these kinds of things. There was a question back there about...
Actually, I have two questions. Are you going to build Mathematica for Android? And are you going to have something like the functionality of Publicon in the next versions of Mathematica?
Sorry.
To interface with LaTeX?
Sorry, the first question was about Mathematica for Android.
Yes, and second about some functionality like that of Publicon. You had this system, but then you discontinued it.
Yes,
but there is still a problem of interfacing with LaTeX, making publications for scientific journals.
Okay, so first question is about Android. The answer is that is our intention. It's the port of the Mathematica kernel to... the port of the Mathematica kernel is comparatively straightforward. The port of the Mathematica front end is quite difficult. The port of CDF to Android is quite difficult. The port of CDF to iOS has taken us about 2.5 years. Android, we expect to go much more quickly than that, but it's complicated. And one of the things that's interesting is that there are new user interface pieces of user interface functionality associated with touch devices. There's sort of a gesture handler that deals with general kind of multi-touch behavior, and that's something that will be supported there. I could show you perhaps. Just to prove that it's real, let me see if I can set this up on my iPad here. Let's see. Let's see, this is probably not the best way to do it, but it might work. Let's see if I can use... I'll tell you what, I am going to... I'm going to quit Mathematica here. Let's go... And then with luck, I can show you. Oh, come on. Oh, there we go. Okay, that's good. All right, hold on. It's very low tech, really, but it's actually easier to understand what's going on an iPad when you see it on a screen like this than if you directly connect to it. Come on, focus. Okay, so let's see. I can show you something that is built using... Okay, so this is a calculator that is not out yet, but it's going to be coming out fairly soon. This is a calculator built using the Mathematica kernel running on an iOS device. And so actually this was so we can, for example, say, integral 1 over x to the 4th minus 1 dx. And there's a lot of interesting interface questions. So there's the result, and then it gives us a predictive interface here, so we can say, make a plot of that, and there's the result. Maybe we can find the derivative of that. There's the result. Let's simplify that. and so on. So this is all running using a native Mathematica kernel running on an iPad and using CDF on the iPad. It's kind of interesting, actually. You can get to so you can get to all these different Mathematica functions here, and you can actually add, if you want. Let's see how well this is working now. Yeah, you can actually get to any Mathematica function from inside this calculator, which is sort of fun, and it's one of our little efforts to help kids who are bored in school using this calculator. If they want to, they can go and explore anything that Mathematica can do. It's part of, we have quite an effort in trying to understand kind of future directions for mathematics curriculums and so on, and this is something that we hope will tie into that. But so that was just to prove that there's something real with iOS. Actually, I could show you, okay, wait a minute, I'll show you just one more thing here. I could show you, let me see, I might be able to show you. Something here. This may or may not work. Oh, this may not work. I was going to try and show you some actual demonstrations from the demonstrations project running on, let's see, I've not tried these before, so I really don't know what's here, but this should be a piece of CDF running on, okay, so now I can say rotate the tetrahedron. Okay, there it is. The diameter of the bar. Okay, so there we go. So this is all now running, and probably I can rotate the thing around here. This is pretty cool, actually. It's a pretty good example. Do all kinds of things here. So that's CDF running natively on an iOS device. Yes.
Может ли Wolfram отображать загруженность сервера Wolfram, например, или кучи на компьютере локальном?
Loaded. Wait a minute. Loaded. I didn't understand. Sorry.
Загруженность сервера Wolfram. Насколько сама система загружена, чисто технически?
Okay, so if you're asking you mean on this? How? No,
about big server.
Oh, big servers. So
how many connections are there on servers? How powerful is the infrastructure?
Oh, okay. Okay. We can okay, that's a good question. It was we have so the main, we have our own infrastructure, and typically we're running about we have our own thing, and so it's some number of tens of thousands of cores, and it can usually withstand. It's never yet been saturated, which may mean we have too much infrastructure. But the scariest time was when the iPhone, when the iPhone 4S first went on sale, when Siri was first being used, because actually you could see in the real-time monitor that we have, because we have pretty good real-time monitoring that we built using Mathematica and so on. You could see that as people started switching on their iPhones, there was an exponential increase in usage, and it started at about midday on a particular day, and it finally turned over to about 7 p.m. And actually the only reason we probably would have run out of server capability had it not been for the fact that there was a problem with AT&T connections in California, which caused fewer people to use that machine, that phone on the first day that it was out. But we have our infrastructure is quite good. Actually, for Mathematica Online and our cloud platform, we're partly using the same infrastructure, but we'll also be able to make use of things like the Amazon cloud, and we will also have an ability to have private clouds where people can have a virtualized version of our cloud infrastructure that they can install in their own data centers, and that's actually already working now. You can also get for Wolfram Alpha. That you can get a private version of Wolfram Alpha. That's primarily been of interest to military organizations in the US, for example, and where they're interested in having queries that can be made to the system without anybody seeing their queries, and so they can get a private version of Wolfram Alpha that's an appliance that's completely inside their infrastructure, and where the only interaction with the outside world is data coming in. Nothing goes out from it. Yes.
Стивен, у меня очень два простые вопроса. Вот вы часто говорите об основных принципах, заложенных в ядро Wolfram Alpha и вообще в Wolfram Mathematica. Вы можете их назвать? Эти основные принципы.
So, for us, I think we have sort of two principles that we maybe three. The one kind of meta principle is implement as much as possible. Just cover as large an area as possible. The second thing is make everything be as unified as possible. So all these different areas are treated in a way so that all the pieces fit together. And that's been something that's been a big personal effort of mine over the last 25 years or so to make sure that, every new function we add fits in with, yes, good, with all previous functions. It's a very interesting intellectual activity because really, you have to understand these areas with great clarity in order to actually, make a design that will fit with what's already there and so on. So that's a second thing. The third thing is automation, to try and make it so that the user really is just thinking about what goals they have, not about how to perform each step in the computation. And kind of the idea there is to build these meta-algorithms that will just automatically figure out the details of what you want to do. So, for instance, when you're doing, graphics and things like that, we want to have it so that we, as much as possible, automatically produce the best-looking graphic. Or when you're doing some computation of some combinatorics problem, we'll, use the best algorithm chosen from a whole collection of algorithms. So that's sort of another principle, is this idea of automation. The notion is most people, most of the time, will want to do things automatically. If they want to, they can drop down to specific methods and start adjusting particular knobs if they know what they're doing there. I think that the one importance of automation is that it allows you to, if you're an expert in some particular area, but you need to use functionality from another area, it's much more realistic to do that because you can just use the automatic functionality from that other area without having to know the area in great detail. This is something that's been sort of a principle of ours from the beginning. You see it, for example, in our handling of numbers, numerical computation. I mean, when if you go, if in Mathematica you, oops, there you go. If you say numerical value of pi. I mean, this is a typical example of the value of automation. So, okay, so we get 300 digits of pi or something. Now let's say let's do the following. So let's have an iterated map. So if we just do this on x or something, well, let's do it. So this is on 0.5. No, let's do this on 1/2, 10 times. This is just some standard iterated map that's going to give chaotic behavior. Okay, so let's say that we start off from, n of, pi over 7 or something, comma 100. Okay, and we do it to 10 digits, 10 times. Now what will happen is, let's do it to 100 times. So what will happen here is that if we were not kind of doing automatic tracking of precision of numbers, if we were just using a machine precision number, let's try out this with the kind of thing that would happen if we didn't sort of automatically do things with numbers. We would just get the same precision at every step. This is completely the wrong answer, because in fact this is a chaotic system that reduces, that kind of eats away at digits. And what we'll see when we do it properly, when we engage the proper automation in the system, is that it will progressively track the fact that you're losing precision. Actually, let's keep going for more than 100 steps, and something more dramatic will happen. Let's say 200 steps here. Let's keep going. It's losing precision more. Eventually, boom. It loses precision completely, and now these are numbers where it says no significant digits are available to display. It lost all precision. But this is something that in Mathematica, it's sort of routine thing for us to do this kind of automatic tracking of precision of numbers, and that's just one of a bazillion examples of kind of automation that we're doing in the system. Yes.
И второй вопрос. Тут все понятно. Закономерно будет такой нескромный вопрос. То есть вы упомянули, что ядро платформы, оно идет не от простого правила к сложным, а формирует группу сложных правил для того, чтобы искать простые решения. Я правильно понимаю? Так, секунду, вопрос, сам вопрос. Вот эти вот набор сложных правил, он у вас имеет единые какие-то законы? Или это набор хаотичных правил, наиболее оптимально подобранных для такого ядра? То есть есть ли набор общих правил, единая система сложного ядра, или она хаотична все-таки?
Okay, so that's an interesting question. So you might ask the question, having seen things like cellular automata, could it be the case that sort of all of Mathematica is just derived from some simple, cellular automaton or something? Well, at some level, the answer is yes, and at some level, the answer is no. So the sense in which it's yes is that everything in Mathematica works by making transformations on symbolic expressions. It's kind of a very simple idea. Everything, if I type in some expression here, the full form of that expression is just this thing that can be represented as a tree, and like that. And anything else that I deal with in Mathematica is similarly represented in this very uniform way as a symbolic expression. So at some level, Mathematica is very simple. It's just an engine that transforms symbolic expressions. However, the thing that isn't simple is all the knowledge of all the algorithms that have turned out to be useful for things that people want to study. And so effectively what's happening is there's a simple underlying framework that then is dealing with this very large collection of algorithms for many different things, and then also now is dealing with this knowledge base about the real world. So, we can say, there's no simple algorithm, for example, for knowing what the shape of a country will be. That's just something that has to come from the world at large. Actually, it's pretty interesting. If you look at, it's kind of shocking. If you look at at a plot as a function of time of the shapes of countries in Europe, for example, it forms a very interesting. It makes it look like there must be a theory of this, because things get bigger, things get smaller, things break off, things combine, and so on. And it seems like a very kind of physics-like process. But that's a different matter. But the main thing here is that. There's a very simple set of principles underlying the system, but then there's a lot of actual knowledge that is of necessity kind of complicated. Yes.
Спасибо. Скажите, пожалуйста, вы не могли бы показать некоторые факты математики 9 в вашем продукте Wolfram Alpha. Вот прямо сейчас интерактивно. Например, число пользователей, насколько оно растет по месяцам, по годам в Англии, в России, в США, в Японии, в Африке. Спасибо. In Wolfram Alpha.
Not in the public version of Wolfram Alpha. We have that data. Actually, we have been building a private version of Wolfram Alpha inside our company that has that kind of information. This is something that we've done now for several. We have a consulting organization that has been building private versions of Wolfram Alpha for different kinds of companies and so on to display their internal data. That's one of the things. It would be interesting to see. We have that information internally, and we have a pretty nice version. We actually right now have mostly Mathematica-based systems that show us that kind of information. There are things one learns, like, for example, when we look at Wolfram Alpha and its use in real time, we can see waves of homework going around the world every day as students use Wolfram Alpha for solving homework problems. We can also see in Mathematica, because it's accessing our servers to get data and things like this, we can see the pattern of usage in different countries, and so we know that pattern, and we know how many legitimate users there are, how many pirated users there are as a function of country. It's not so great in Russia, but it's getting better. The better it gets, the more motivated we are to do great things in Russia. I think so. Those are, there's all sorts of information that Wolfram Alpha is a very powerful platform for dealing with internal information for companies and other kinds of organizations, we're going to be doing a lot more with that in the next few years. Yes.
About database that you use in Wolfram Alpha. Mm-hmm. If we are making some economic research, some social study research, how and why we can believe in the data that your system provide? Can you provide us some insights how you collect, analyze, and check the data before use it in Wolfram Alpha?
Right. So, we try to get our data from the best primary sources. We've spent a lot of effort kind of making relationships with lots of organizations, whether it's OECD or the World Bank or the UN or the Federal Reserve in the US, all these different kinds of organizations. We actually have a data summit conference every year in Washington DC, where we bring together people who run these large data collections. It's been a very interesting conference because these people have mostly not met each other before, so we've made a lot of effort to really get to know and make relationships with these different sources of data. Now the second thing is that we can check this data because we can cross-check information from different places, and we're in a unique position to do that. And we've found more errors in these kinds of data sources than anybody else by a huge factor. In fact, it always shocks the people who give us, for example, financial data, that we're giving them all the time, a stream of errors that we're finding, and they say, nobody else finds these errors. Well, the reason they don't find them is because they're not computing things from the data in the same way that we are. Now, another question is if you ask something like, I don't know, let's ask, let's just try, I have no idea if we have, let's try something like this, and let's see, okay, so there we get a result. Now, what we should have here, some of these results have, there we go. So here we have a little thing that says sources, and so here, when we click that thing there, it'll say the external sources, Food and Agriculture Organization of the UN, FAO, STAT, and so on, right? So this is something we've been progressively adding. We'll always have a thing at the bottom here that's a general list of sources associated with everything that's on that page. We're also adding what we call microsourcing, which is this ability to know for some particular plot or something what the source of that data is. So I think this is, I think we, think we're doing a pretty good job of this. One of the issues is in economic, so the main issue about data is, can you get data on something at all? People often say, how do you make sure all the data is consistent? That's a luxury, because the first issue is there data at all on something? There's usually at most, one source, and often there are zero sources. So first we have to get the data. Sometimes there's multiple sources of data. So for example, in economics, there are multiple sources of data for things like, even some population data, there are multiple sources. Some GDP data, there are multiple sources. That's been a complicated issue for us, trying to get a consistent set of sources so that we can have the relations that should be true between different quantities actually hold. And we've had to make definite decisions about going with one source of data rather than another source of data, and we try to do that in a sensible way. I mean, if we say, let's see, what is a port city? Let's say, this, I don't think this will work, but if we say, one of the issues is, how do you give... Okay, what is the nearest port city to... I should be able to ask that. I need a city that's on okay, wherever. Okay, so let's try... Oops. Maybe. This is... Okay, maybe there isn't data for Russia for these things. Oh, come on. If this doesn't work, then I'll know there's something else going on. Okay, at least we have data for this. Okay, so this is just what is the current tide in New York City, right? Well, it turns out that if you go and look in New York City and you see how high is the water, this will be a good approximation, but it may not be exactly the right answer. And so one of the things that we try to do is to give sort of appropriate footnotes. So it says computed using historical data, not taking into account weather, etc., and those kinds of things. So we try to give a footnote that represents something about what the possible problems with the data might be. And so we know perfectly well that for some economic data and some socioeconomic data in some parts of the world, the data will be inaccurate. We know that, but the best we can do is to get data that comes from a UN census or from a census or something like this, and so we try and give a footnote that gives some idea of what the possible inaccuracies of the data might be. But our main goal is to just use the best primary sources of data, and we think we've done a pretty good job of that. And we think that for purposes of, Wolfram Alpha is being pretty widely used now in economic research, but also by lots of policymakers who are interested in just figuring out, what's going on with something. One of the interesting challenges right now is which country will be the first country that is fully computable, in the sense that all of its public data is accessible in a computable way, so questions can be asked. And there are several countries that are kind of look like they may be the one to actually sort of take the plunge first and actually get all of their government data into computable form. Which will be quite interesting, I think, because it will allow it has quite a lot of economic value to be able to let anybody ask, detailed questions. Often governments collect huge amounts of data, spend a huge amount of money doing it, and then nobody uses that data. And this is sort of a way to deal with that problem. Yes.
Вопрос.
Okay, there's a problem that
Вопрос касается визуализации, возможности визуализации с помощью системы Wolfram Alpha. Вот может ли эта система дать образ простому понятию, например, ребенок? Или более сложному лингвистическому высказыванию, там, солнце взошло, пошел дождь. Или создать фильм на основе романа там, «Война и мир».
Okay, all right. So those are that's a very high bar. I would say that Wolfram Alpha is getting pretty widely used now in education down to fairly low levels. Right now, Wolfram Alpha is only available in English. The first non-English version is one in Chinese that will come out later this year. We hope to do versions of Wolfram Alpha for all languages. Typically, that requires finding a partner within that country that can basically, put up the funds to do it and help us to get access to local data in that country. But at least, so kind of the here are some examples of some sort of lower level things. So this is you can do step-by-step versions of simple arithmetic, or you could do things like show me a picture of an aardvark. Let's see what that does. I hope it works. There we go. It's a rather ugly animal, but now, and then in terms of, let's see, let's try it. Let's see what it knows about War and Peace. Okay. Knows the book. That's a good start. It doesn't seem to know much about it. Knows a little bit more about something like a Shakespeare play. If I say something like that, it's probably going to show me. It knows the text of the play, and so it knows, for example, it kind of can grind it up. Let's see. Let's try that again. It should be able to show me things like. Let's hope that doesn't time out. Let's see. Yeah, there we go. So this is showing me as a function of time through the play, when was Hamlet speaking, when was Polonius speaking, and so on. Usually it's a bad sign in one of these plays when there's a character who speaks a lot for a while and then stops speaking. That's usually means something not very good happened to that character. But that gives some indication. I mean, and in fact, from this one can start to, for example, build up the social network of characters in Hamlet, things like this. Those are some indications of things one can do. Now, one thing I might mention about kids is there's a question of what programming language should you teach kids? And I think we're going to make a very strong case that the Wolfram language is kind of the best alternative right now. And the reason is that it's the only language that has all this stuff built into it. So it's the only language where one can really expect that with a fairly small program, one can already do some very interesting things. And in fact, we've done quite a lot of experiments now on teaching Wolfram language to kids. We have a Mathematica summer camp. Actually, it's happening in about 2 weeks from now for this year, where we get high school age kids to come in for 2 weeks. And at the end of it, they are quite fluent in producing Mathematica demonstrations and things like this. I think it's with the programming cloud, for example, we will have the opportunity to expose a much broader range of people in the world to the Wolfram language, and we hope that that will make it easy for lots of kids to learn programming through it. So that's another direction that we're going in. I think the ability of the Wolfram language to access our knowledge base and write programs about real world things, like about making a movie of sunrise and sunset and so on. It's that's an interesting thing. I mean, I've been able to do some experiments. I have 4 children of my own, one of whom, a 14-year-old, is a good Mathematica programmer. The other children use Wolfram Alpha but won't use Mathematica for one reason or another because they think programming isn't for them. But it's been interesting to see the now 14-year-old learn to use Mathematica and learn lots of mathematics through using Mathematica. In fact, he will say that he doesn't really believe in mathematics because he doesn't know how to do any of these computations by hand. All he knows is how to compute them by computer. Actually, I'll tell you one story about that actually might relate to your thing about the sun and so on. My older daughter, who's 15, had some project from some online course she was doing of making some sundial based on some ancient Greek version of sundials. Okay, so she is a good student of mathematics and calculus and all this kind of thing, and so she's trying to work out, what will the path of the, given the path of the sun, how do you set the markings on the sundial and things like this, and was having a hard time doing that using trigonometry and all these kinds of things. Well, my 14-year-old says, look, this is actually easy. I can easily write a program that does this. So it took him about 10 minutes to write a program in Mathematica that, correctly figured out. I mean, I would suspect he used, we could probably, there's a function, astronomical data, that knows about the positions of the sun, and then there's geodetic stuff that knows about how to project that onto the Earth, and pretty soon, even if you're 14 and so on, it's not very difficult to write a program that makes a nice little 3D picture of how the sundial should work. So that's an example of kind of perhaps a modern version of what one can do, kind of using this kind of technology in education. And it even relates to the sun, and he even made a movie of the motion of the sun on the sundial. So it has some real relation to the question asked. Yes. Can you ask it in English or?
Excuse me.
Okay, back there. Yes.
Okay, thank you. Hello, I'm Alexandra, and thank you for your presentation. And I would like to ask you if to compare this Wolfram Mathematica with some other programs, statistical programs like SAS, SPSS, econometric use. Can you tell us some pluses and minuses? For focusing, for analytical, some analytical of statistical data.
Okay, so in the area of statistics, we are a comparative latecomer, in the sense that SPSS was first developed in the 1960s and so on. We have a great benefit from being a latecomer, which is that we get to use much more modern algorithms, much more modern methods, and also. The algorithms that we now use are algorithms that would have been inconceivable when programs like SPSS were developed, because they rely on sort of other kinds of algorithms, like they rely on computational geometry or graph theory or something like this. That's something that just wasn't something you could expect to use in a sort of simple numerical program back in 20, 30 years ago. So in terms of, we've been sort of progressively working through all the different areas of standard statistics to support. Let's see. If we say I'm not the biggest expert actually on all of our statistics functionality, but I don't know, let's take linear models, for example. So there's a whole elaborate system for dealing with linear models that is pretty general. And what's nice about it is that by using the symbolic capabilities of the system, things get a lot cleaner. So let me show you a very simple example. Okay, so let's say that we have some data. Let's make up some data. So let's make a table of primes. N goes up to 100, let's say. Okay, so there's some data. Now let's say I want to do, let's just say find fit to that A plus BX plus C log X, for example. Okay, so then that's a pretty straightforward thing. That gives us the best fit. But we can, I'll tell you what, let's do the following. Let's say interpolate, interpolation of %11. Okay, so now what this gives us is this function that is an interpolation function, and we can now use that function. So let's say we call that function ff or something like this. Now we can use ff as a function, so we can say ff of 6.7, for example, and it just gives us a value. Or we could say plot ff of x. X goes from 1 to 100, and now we'll get that function. We can just plot that function, or we can say plot the derivative of that function, and there's the derivative of that function. So it's very convenient that we can take these results from, in this case, an interpolation, but it could be a statistical fit or something like this, and treat them symbolically, and then do further operations on them. So that's an important kind of thing that becomes possible. If you look at, for example, let's say, let's look at something like this. Well, if you look in the area of statistical distributions, for example, you'll find that in Mathematica we have, I think, the world's most complete collection of these kinds of things, along with all sorts of analytical properties of them. So we're not just doing numerical computations. You can do analytical computations. You can do things with random processes. You can do all kinds of different things. I would say that the real killer in the real thing now is being able to integrate statistical computation into a broader selection of computations. Being able to do things like image processing and network analysis as part of the same system. And being able to do, for example, natural language processing. Like, for example, the stuff I was showing you for Facebook was using natural language processing integrated with statistics, integrated with machine learning, integrated with visualization to produce a result. And then, even more than that, things like CDF, being able to make interactive documents, that's another important capability. Being able to do things in the cloud, being able to automatically deploy things. So most of the things that I'm now describing are things that the traditional statistics packages are just, it's not in their world. They're not, that's not the kind of thing they can do at all. In terms of the raw, do we have this statistical inference method or that statistical distribution? We're doing really well at filling in sort of all the different methods that people have traditionally used. There are some areas where I have to say I'm not that enthusiastic about implementing them because I don't think anybody's ever cared about them for 30 years. So those will probably be the last to get implemented. But all the kind of traditional linear models, regression, all sorts of statistical inference tests and so on. That's all there. Again, particularly nice stuff that I might comment on. The analytical treatment of probability is pretty interesting. That I showed you an example of, although it took me a while to get it to work. But that's another pretty interesting area. So I think what we're seeing is that sort of organizations that are doing data analysis, are starting to do data analysis now, are really being very successful with the tools that we have. If they have a large body of existing code, then that's a separate issue. One of the things that was actually added in version 9 of Mathematica was the ability to call R functions from within Mathematica. So if you have code in R, you can just use it in Mathematica. In fact, I think the environment for using R in Mathematica is probably nicer than the environment for using R in R. It's a very nice way to use functions from R. I think that what we'll see in the next year or two is a big shift of lots of people lots of people doing data analysis using Mathematica because, well, for a variety of reasons. First of all, because the core capabilities are good, but also because all of these deployment mechanisms in the cloud and connecting to devices and things like this are very clean in our technology stack. So that's And there's somewhere, if you really want the feature comparison of all the different types of models and so on that we support, somebody has that. I don't know it, but somebody has that, and we're steadily sort of filling in all the boxes, so to speak. Yes.
Excuse me. You showed us some calculations, or, for example, taking integrals in alpha. And I wanted to ask, it shows steps which human would do if he or she would have been solving this equation or integral. If you give these steps, why don't you use them for solving this integral? Why do you use some other method? Because it's kind of strange.
Okay.
And I have another question. You are a physicist, as I read in Wikipedia. For computing observed data, experimental physicists use Origin Pro and other programs like that, and they don't use Wolfram. Why don't you want to take over this industry? Because actually, Origin is quite bad program, and I would like something quite nicer to see in this area. Thank you.
Okay, so first question is about steps. The reason we don't use the steps that we make up for humans is because they're pretty inefficient. You know, when we do an integral, the most common method that we use is the following thing. We convert the integral to a product of hypergeometric functions. Then we use some general theorems about integrals of products of hypergeometric functions. Then the big challenge is to convert the result back to something that a human will recognize in terms of simple functions. But that methodology is very powerful and allows us to take, large number of integrals and just immediately solve all of them. The kinds of things that humans use are based on particular tricks that work in particular cases. I mean, if I type in, let's say, integrate. Let's say I say something like, sine of log of x. I have no idea if that integral can be done, but let's just try it. Okay. It says it has a step-by-step solution. That integral is easy. All right. So that particular one, it will have a step-by-step solution, and it can give us something involving substitutions. I think I might even maybe be able to do that integral by hand. Okay. Let's make it harder. Let's say integral of log of sine of log of x. Can that integral be done? Okay. Yes, there it is. So it comes out in terms of hypergeometric functions, and there's no hope of giving a kind of human step-by-step, school-appropriate version of how to do that integral. That's something that's really just quite outside of that kind of thing. So that's the reason that we don't use, that we're just creating those things to make it clear for humans if humans want to learn how to do integrals. In terms of physics and experimental data and so on, the fact is the number of physicists who use Mathematica is unbelievably much larger than the number who use something like Origin, which is a quite old program that has a quite small user base. It is something that certainly I wonder about. I look at these programs that have been developed and are often quite old for doing particular kinds of things, like specifically for making plots, or specifically for doing numerical linear algebra or something like this. And I say, why don't these people use Mathematica? And the answer tends to be, well, because they started using this other thing a long time ago, and they are not, they don't want to learn something new, etc., etc., etc. I think progressively those issues will change. I mean, what's been interesting is that Wolfram Alpha, for example, is a zero learning product. That is, you don't have to learn anything to use Wolfram Alpha, and so that means that people, millions of people start to use it all the time, and they don't have to learn anything, and they can just use it. So now the challenge for us is to take that zero learning product and apply that same methodology to all of our products, to Mathematica, CDF, and so on, to make it so that all of those can be used by people without any cost of learning and so on. And that's something that we are increasingly going to be doing over the next few years. So these things like the predictive interface in Mathematica, the free-form input in Mathematica, these are all parts of that. I think what will probably happen, my guess is what will happen in the industry in the next few years, is that as things move to the cloud and mobile, people will reevaluate the tools that they use, and I suspect that we'll pick up a large number of users of these older tools because basically they're making a change because they're trying to move to the cloud, for example, and for example those tools just don't exist in the cloud, or they're going to make a change anyway, and then they'll end up figuring out that yes, we can do really good things with our technology stack. At least that's my theory of it. It's always hard to predict these kinds of things. Yes, please.
Господин Вольфрам, как я понял, основной подход – это от общего к частному. А насколько такой подход эффективен или сравнивали ли эффективность, например, в играх? Шахматы, го. Можно ли там предсказывать ходы и насколько эффективно с другими стандартными, традиционными программами?
So, well, the things that we do have little to do with something like chess. But I mean, chess is something where there are fairly specific computational methods for doing it. But the general approach that we take, okay, so in Mathematica, we try to have a very general system that will do a lot of different things. You might say, surely a specialized system will be faster at doing the particular thing that it's specialized to do. Let's say it's specialized to do graph theory. Surely it'll be faster than Mathematica, which is a general system. Well, in the past you might have been right. Today you will be wrong. And the reason you're wrong is that the fastest algorithms end up making use of things that come from many, many different areas. And that means we can implement these things, but somebody who has a specialized system that's just dealing with graph theory, let's say, can't do that. If they need some algorithm that involves symmetric polynomials and some kind of algebraic decomposition of, something or other, something like this, they can't do that. They'd have to write another 1 million lines of code to be able to do that. And they won't do it. They'll just use things which are specifically about graph theory. And so it probably in the last 10 years, this has really been a change that's happened, that a specialized system can no longer, the quality of algorithms that exist today is such that most of the best algorithms make use of things from other areas. And so that means that you just can't do it in a specialized system. You have to have a general system to do it. And that means that we can do things that are when we're doing a numerical integral, for example, we can do a symbolic algebraic transformation on that integral that makes it incredibly much easier to compute the integral. But if you have a system that is just doing numerical computation, you can't make such a transformation. So now the only issue then is when we represent data, we're representing it in a general way, and there's a question of how efficiently can you get that data into kind of a low-level form where it's optimal for these algorithms. And that's something that is part of our sort of push for automation. Underneath the way that we represent data, if you see a list of numbers in Mathematica, there are actually several different ways that list could be represented internally that we use for doing that are optimizing it for particular purposes. Another thing to understand is that this is a very interesting question of whether it's more efficient to have a general system or a specialized system. It's really been something that I wasn't particularly expecting this, but it's something that's happened in recent years, that it's just more efficient to have a general system. Another thing to say, when you look internally, if you look at the internal code of Mathematica and you look at an algorithm for doing something, I don't know, some operation that you think is quite simple, like let's say multiplying numbers. Okay, so there is a general algorithm for that, but it turns out to make the thing efficient, there are zillions of special cases that have to be broken off that are what help make the whole system really efficient. So, in fact, one of the things that's sort of a the elementary, let's just implement this simple algorithm thing is rarely what we actually end up doing. We end up with many different cases and lots of code that deals with special cases to optimize what's being done. And we're able to make use of sort of other areas of functionality in the computations that we do. Yes. Sorry. Oh.
Sorry. Thank you, dear colleagues. Dear colleague, thank you very much. I would like to thank you for your presentation. Sure, it was very, very interesting, not only for me, for all of my colleagues too. Thank you very much. And my question is about using features and capabilities, Wolfram software.
I'm sorry. Question. Could you just repeat what the question was about?
Yeah. My question is about using features and capabilities Wolfram software for real business. How can we use Wolfram for example, for marketing research, for example, as business intelligence system, for example, as a management decision support system? Could you compare such software as Wolfram and, for example, SAP or sub-business intelligence systems, sub-business objects, for example? Can you give us maybe some success story about using Wolfram software for real business solutions? Yeah? Maybe best practices.
Right. So many organizations end up using our software. What happens? So here's what typically happens. The R&D organization will always use it. So if you look at the Fortune 500 companies, probably I would say at least 90% of them, you'll find that the R&D organization uses our systems. Now the question is, do people other than the R&D organization use it? And that's something that's been greatly expanding in recent years. And I think as we make it easier to deploy our solutions, that will expand a lot more. In terms of success stories, well, there are lots. We have a consulting organization, for instance, that builds out, kind of large-scale systems. Which ones can I talk about? Well, I mean, there are success stories in. I'm thinking, I'll give you some examples. In the pharmaceutical industry, there's a large clinical trials data system that's built using Wolfram Alpha and Mathematica, used by one of the world's largest pharmaceutical companies for their internal data on clinical trials. That's one kind of example that comes to mind. In the area of pure sort of business analysis, there actually are several projects going on right now where the internal data of companies is being put into Wolfram Alpha form. The thing that's really exciting about that is it allows one to sort of compare the private data of those companies with public data. It allows one to ask questions easily that would have previously taken, a custom study done by some internal group and so on. I can mention one example that I just happened to see last week, that our consulting organization did for it's a company that does something quite mundane. It deals with dentists' offices. It owns a large number of dentists in the US. And the problem was that they have lots of data coming in about when people are coming for appointments, when appointments are being booked, when they're not being booked, all these kinds of things. And the question was what to do with all this data. And this was an industry where nobody had really done any kind of quantitative analysis before. And the results that we got with, it's basically primarily Mathematica programs, seem to be from what I gather from that company believes it's a pretty transformative thing that's been possible now, using our technology to basically ingest all the data, do a bunch of analysis, and then in that case produce CDFs that can be deployed in the field for their various branches and so on. So that's a very mundane but very practical example. in general, what we found is that right now, as I say, we've had terrific success for many years in the R&D sector. It's been something where with our own consulting organization, it's been very interesting to see what's involved in moving that to more production environments, and that's been one of the things that's driven our efforts in making these different deployment channels, because we can see that these are needed over and over and over again, and that's something that will be sort of automated in the products that we have coming out in the near future. I would say that for our own, if you look at the internal reporting that we have, for example, in our company, using our technology, with what we have had in the past, using things like, using the standard Oracle, business objects, crystal reports, kinds of tools, the stuff we have now is spectacularly much better than we were ever able to get. So at least we have our own data point for what can be done in that way. I would say that, okay, I'll say one more thing. One of the things that we're doing as a company, so this is a slightly different thing to talk about, but we've been a quite successful company for a long time, and I've had a simple life because we are a private company without any outside investors, so we get to do long-term R&D and things like this, which is great. One of the frustrations of being a private company is that we only have 700 employees. It's we can only do a certain number of projects as a function of time. So we actually decided to take a new approach, and we're starting a separate company, which is basically a company to launch spin-offs from our company, and we just raised a rather large investment fund for that launchpad company that we'll be using to spin off a sequence of companies that do kind of specialized things based on our technology stack. The first three of those companies, one of them is for learning systems for education. One of them is actually a business systems company. One of them is a medical diagnosis company. But the business systems company, its objective is to take our Wolfram Alpha technology stack and to make it so that it can be connected in a turnkey way to things like Oracle and SAP and so on, so that you'll be able to take a large kind of a large business system that's running and automatically put a layer of Wolfram Alpha capability on top of it, which is something that we've done as a custom thing for a bunch of specific organizations, but we've had many requests for this. So this is something we're actually spinning off a company specifically to do this type of thing, and there'll be more to say about it in a few months.
Только два очень коротеньких вопроса. Можно? Вопрос первый. Вы прибыли сейчас в Россию как бизнесмен или как человек, который хочет показать хорошую, действительно хорошую систему? Как бизнесмен или как ученый, назовем так?
Actually, I'm in Russia because for about 20 years I really didn't travel at all, and my children are now of an age where they're very keen on traveling, and they tell me, we want to go to this place, this place, this place, this place. So I'm in Russia, number one, as something of a tourist, but in terms of I have an interesting position because I'm a person who's interested in ideas and creating technology and so on. I also am a person who runs my own company. I might have been my own personal greatest interest is in building technology and developing ideas and so on, but I found that the most efficient way for me to get my ideas turned into reality is to have a company to do it, and the most efficient way to have such a company is to run the company, so I'm in this position of being a person who spends most of their time originating ideas, but also runs a company to try and turn those ideas into reality. I'm not I have to say that My personal interest tends to be in the development of ideas rather than in, my attitude is I'm trying to build things that are useful for as many people as possible. And I try to communicate a bit of what's useful about them, but the details of how products should be licensed to people and all those kinds of things, this is not what I'm an expert in. And in fact,
Хорошо, вы действительно великий оратор и великий человек. Но вопрос второй-то все равно вытекает из вашего первого ответа, хотя я просил всего лишь да или нет. Скажите, вот что вы хотите предложить для российского бизнеса сегодня, в этом году, на этот сезон, чтобы внедрить ваши идеи именно в российский бизнес? Сама система прекрасна, но вопрос стоимости, вопрос последующей эксплуатации, поддержания и стоимости кадров, которые это дело будут обслуживать. Одной из проблем, вы прекрасно знаете, это отсутствие поддержки национального языка в вашей системе. Российские начальники, российские менеджеры этого очень не любят. Что-то планируется в развитии? Все, спасибо, больше вопросов не будет.
Right. So, it's interesting. One thing that we've found in working in different countries is we have to have a strong partner in that country to be able to do a good job of delivering our technology in that country. I think that, for example, for Wolfram Alpha, we're just starting the process of translating it, of localizing it for different countries. It's a very complicated thing to localize. It could be the most complicated software anybody's ever tried to localize because it's understanding natural language in a particular language. It's being able to generate results in that language and so on. In China, for example, the way that we've done it is by working with an organization there that basically, we have a joint venture with them to create the Chinese version of Wolfram Alpha. That's what we would hope to do in other countries, including perhaps Russia. And that's, I think, the most effective way to do it because, we need sort of local help to be able to make a good version of something like Wolfram Alpha for a country like Russia. And that's the challenge that we have there. So, I would hope we're going to be, as I say, Chinese is the first place where we're doing this. Several other languages and countries will be coming soon. I hope Russia will be one of the ones that comes at some point. But the challenge is to make the right arrangements, find the right partners, and so on. And that's not particularly my part of the activity. I'm mostly the guy who tries to figure out the technical ideas and the overall strategy. I'm not typically the guy who figures out the details of partnerships and so on. That's a very requires lots of skill that aren't necessarily my top skills. Yes, please. Oh, sorry. No. Please, you have the microphone.
In Russia. Во-первых, большое спасибо вам за прекрасный и мощный продукт «Математика». А вопрос у меня в следующем. Вот технологии IBM Watson и Wolfram Alpha, они немножко различные. Есть ли какие-то наметки, идеи по их интеграции? Спасибо.
So, actually, I have a picture because people asked that with some. There's a picture that. Watson is really a text retrieval system. And what it's doing is to take natural language text and try to, match up, much as a search engine does, a particular query with something that exists in the natural language. what we're trying to do is to turn knowledge into something computable, to actually have an algorithmic representation of knowledge from which we can compute things. So we're trying to do things where we can generate new knowledge rather than just retrieving something that's already been written down. Actually, the place where these kinds of technologies will probably come together is in doing data analysis of natural language texts in Mathematica and Wolfram Alpha. So, in a sense, the way that one can think about well, for example, that we did that for Facebook, for all those, Facebook wall posts and so on. We were asking the question, we can answer a question like, what do people typically talk about on Facebook? So, for instance, I don't know if I have one of those. Yeah, there we go. So, this answers the question, what do people typically talk about on Facebook? That's a kind of question which is sort of a mixture of text retrieval and other kinds of algorithmic computation. I suspect that when you look at the web, for example, what people are typically doing on the web right now is to ask the question, is there a web page that matches these keywords? Another question you can ask is, what does the web think about such and such a thing? So a very simple example would be if there are two spellings of a word, you can see which one is more common on the web. But another question would be, are people talking about, are the people who are talking about such and such a kind of drug mostly, doctors, or are they mostly, some amateur medical enthusiasts or something? Or is it the case that, some particular product is more popular in Brazil than it is in some other country? These kinds of things. These are questions that you can answer by doing analytics on the natural language that exists on the web. So I think that's the place where we'll start to see things come together. Let's see. Yes.
Мой вопрос вызван примерами из вашей презентации, где были числа с десятками цифр. Прежде всего напрашивается, когда мы заранее знаем, что там точность потеряна уже во втором-третьем знаке, зачем тащить так много? И как ваши программы показывают, если известно, что точность потеряна, вот они реагируют как-то или нет этой реакции, просто выдаются длинные списки цифр, и пользователь сам уже должен что-то с ними делать. Но вторая часть вопроса для меня более интересна. Что делать, когда количество цифр измеряется мегабайтами? Уже лет 15 известны башенные системы счисления, которые позволяют такие числа, скажем так, разумно записывать. Правда, насколько мне известно, нет алгоритмов, которые позволяли бы с ними, хотя бы арифметические действия выполнять достаточно точно. Вот это направление, оно вам интересно? Как-то оно у вас присутствует или планируется, или совсем выпало? Спасибо.
So, okay, in terms of numbers with low precision, let's see. So I could take a number like pi and I could say just have 5 digits of precision. Now if I try and do something like, let's say sine of 200 times that. Okay, so what it will do here is it will say, well, it's about 0, but it only knows that to effectively 3-digit precision. It says 0 times 10 to the minus 3. So let me try a different example. Let's try taking line 18, and let's say we do, sine of 200,000 times that. Okay, it says, forget it, I don't know what the answer is, because that amount of precision in pi is not sufficient to determine what the value of sine 200,000 times that number is. So what we're trying to do here is, following this automation idea, we're trying very strongly not to give the user something that they then have to interpret. We're trying to automatically say, no, you can't get an answer here. So that's I think that was what you were asking about, low precision numbers. As far as high precision numbers are concerned, we have really very good algorithms, I think, now. Some of them are our own, some of them come from open source libraries and things for dealing with numbers with very large numbers of digits. So I'm sure, let's see whether I can blow up my computer here. Let's try, okay, let's see how long it takes. That was pretty good. That was 0.6 seconds to get 1 million digits of pi. Okay, let's tempt fate. And let's just try going to 10 million digits. I don't know what will happen here, but okay, that wasn't bad. 8.7 seconds to get 10 million digits of pi. So, we can deal with pretty large numbers and large numbers of digits there. Other, yes, please. Oh, whoever has the mic. Yeah. Go ahead.
You have mentioned today that Mathematica stems from your own scientific research. And in your book, A New Kind of Science, you wrote that you are looking for fundamental laws of physics and trying to look for computational laws of the universe. And according to your view, our universe is a giant network of elementary units which interact with each other. And so you strongly believe that our universe is digital, but maybe in fact it's analog, and the digital representation and Boolean logic is only a crude approximation of it. Thank you.
Well, so the thing that I've been interested in is, after you've seen all the things that can happen in systems like cellular automata, the obvious question is, could our whole universe be derived from some simple rule? And so I've been, if there is a simple rule, it has to sort of exist underneath traditional notions of space and time and so on. And my favorite kind of approach is to think about networks that are just consists of nodes with connectivity information. No geometry, no topology, just nodes with connectivity. And what ends up happening is that on a large scale, a network like this could behave like a one-dimensional system, a two-dimensional system, a three-dimensional system, whatever. You can go ahead and ask sort of what possible rules might be used to evolve such a system, and you can kind of enumerate possible universes. What's interesting is that even among the first few rules that you look at, you're getting very complicated behavior. Whenever you can get behavior where you can do a mathematical analysis of the behavior, you pretty much know it's not our universe. It's too simple to be our universe. But there are plenty of examples where you get very complicated behavior and where it's really an interesting question whether we've already found something that can represent our universe. Now, is this right? Or is our universe actually constructed with something that can't be represented using these kinds of digital structures? I don't know the answer, obviously, but it seems like it's a good thing to try to investigate, given that we can search this kind of computational universe of possible digital universes. It seems worthwhile to try and do such a search to see whether we can find our universe among those simple computational universes. And what's been exciting is that lots of features of our universe, like Einstein's equations for gravity, special relativity, some features of quantum field theory, it's been possible to see those arise from these very simple underlying systems. It's sort of a surprising thing that from such a simple, discrete underlying system, you can get kind of continuum features of space and so on arising. And that's kind of an encouraging sign that this might be on the right track. But we won't know until we actually either have the definitive theory of the universe or can prove that there's some phenomenon that can't be represented this way. We won't know what's true. I think it's the fact is, if we're going to be able to understand how it works, there had better be some digital symbolic representation for it. Right now, we don't have any mechanism, any way of thinking about things that isn't ultimately either digital or at least symbolic. I mean, whether it involves continuous functions or discrete functions, that's not really the issue. The issue is whether it, because, if we could have a Mathematica program that represents the universe and it's got all kinds of hypergeometric functions running inside it, there's nothing difficult about having continuous functions. The issue is it a program or is it something that can't be represented as a program? And that's, I think my theory of it is let's try the program thing and see whether that works first. Okay, I don't know whether we may be running out of time, unfortunately. But please, okay. Whoever has the microphone should, let's see. Okay, back there, yes.
First of all, I want to thank you for interesting and informative novel and some question around your system. First of all, I want to know, do you know how many exactly programmers work in your company? What is an average time for producing? This means I'm only producing the built-in function. Anything. And can you explain us what is the mechanism of create a Mathematica function? Because we see only the result of work of this function, but what about the process of creation?
Okay.
Thank you.
That's an interesting question. Okay. How many programmers work at our company? Depends what you mean by a programmer. I think out of 700 people, about 500 are involved in producing products, and 200 are involved in things to do with supporting products, distributing products, and so on. So now, what do programmers do? There's a much smaller group that works on core kernel functionality for Mathematica. For example, there's a mathematical algorithms group, I don't know, 30 people maybe of that order. But those are people who write the underlying algorithms. Then there's a group that does testing, which is about the same size. And then there are, the process of putting a mathematical function into Mathematica is an interesting issue, okay? So actually, I'll tell you a slightly funny story. There's a person who's been a long-time employee at our company who's actually... I guess, Russian fellow who named Oleg Marichev, who was, before he came to our company, he had a long career as a professor producing very large tables of integrals and books about mathematical functions. And he has been, for 20 years now, working at our company, sort of putting that kind of knowledge into Mathematica. And one of the things that happens is that he will say, we must add a new kind of special function. And he then writes up a sort of a proposal for these special functions, and has, in some cases, he's had a multi-year campaign because he really wants some particular kind of special function, because if we add those, we get to be able to do lots more integrals and things like that. And so the question then comes up, what is the cost of adding a new special function to Mathematica? And so we know a little bit about that, because here's why it's difficult. Right? So you have a function. So, for example, one of the ones that Oleg has been very keen on is the thing called the FoxH function. So the question is, what's involved in adding it? Okay, so we have to be able to evaluate it numerically. That's pretty difficult in many cases. In many cases, we have to invent algorithms. Sometimes there's a series expansion that works for some simple cases, but then in more extreme cases, it doesn't work. You have to be able to derive some asymptotic expansion, et cetera, et cetera, et cetera. So that's a big block of stuff. Then there's, we got to be able to find derivatives of this function. This function can be a solution of an equation. We've got to plug it into the equation solving systems and so on. It's got to be connected to all these other things that the system does. Then another question is, we've got to be able to test whether we're actually getting the right answers for this function. And so, years ago, we had digitized all of the standard mathematical tables books. But any of the functions that we're putting in now, nobody's made a table. So we're kind of on our own to be able to test it. So that means that we effectively have to derive lots of theorems about the function and then see if they're true for the numerical approximations that we have, things like this. So there's quite a lot of, it depends on the function. I mean, but I would say that a big function that's one of these ones that's in a different area, this is probably many person months of work, if not a person year of work. We've got a lot of technology now for adding functions, but it's difficult. Now, for example, we were adding in Wolfram Alpha, we have some of the old-fashioned trigonometric functions like have a sign and things like this. These are fairly easy to add. And these are probably a matter of less than a week of work per function. But that's kind of the exceptional case, because those are just ones where it's just a name for, 1 minus cosine x over 2 or something like this. But it has certain special properties and so on. But it's an interesting question, how, we'd like to, we have a lot of internal metrics. Actually, we know this much better for Wolfram Alpha than we do for Mathematica, because we've done much more extensive code analysis there. When we add a new domain to Wolfram Alpha, we know, well, one feature of Wolfram Alpha is we have a user-generated to-do list, because we can see all the queries that people have made that didn't work. And so we have, we can see there's 1 million queries that didn't work in a particular area. And they didn't work because we didn't have some knowledge in that area, so let's add that knowledge. Now, how long is it going to take to do that, et cetera, et cetera, et cetera. This is something where we have some decent metrics. And it's always kind of... it's always shocking that after you've done thousands of different domains, that every new domain that you add still takes a significant amount of time. There are still new different issues that come up, even though you can make use of a lot of frameworks that have been developed before. Are we running out of time? No. I can go on. I'm happy to go on. Yeah, please. Yes. Yeah.
С точки зрения вашей технической стратегии, вы делаете так, чтобы Wolfram Alpha был максимально доступен, чтобы не нужно было ничего учить. Как вы считаете, нужно ли саму систему Wolfram Alpha чему-то учить дальше? В этом городе недоступна информация по портам, да, и приливам, как вы заметили. Но в этом городе работал такой ученый, как Менделеев, который сделал периодическую систему элементов, ей пользуется весь мир, говоря о масштабе использования вашей же системы. Как вы считаете, нуждается ли Wolfram Alpha в обучении, нуждается ли она в единой системе, такой подобной, как система Менделеева? Вы же создаете единую систему алгоритмов. Единая система в любом случае нуждается в единой системе. Вопрос понятен? Или это тяжело?
Not quite. I don't quite understand. But let me.
Я могу пояснить.
In terms of how do we get information about tides in the port near here. There's got to be some sensor measuring this, and then we've got to get that data. I mean, there's no alternative to that. We can do some computation by solving differential equations for bodies of water and things like that, but ultimately, not wrong question.
Заключается в том, что нужно ли вашу систему, как вы считаете, чему-то учить? Нужно ли для нее создавать единую систему каких-то представлений, таких как система таблицы Менделеева? Вы же строите единую систему алгоритмов. Как правильно заметили, указав о вашей книге, что вы строите единую систему алгоритмов Вселенной. Считаете ли вы, что необходимо создавать такую единую систему, подобную системе Менделеева, и готовы ли вы вашу Wolfram Alpha чему-то учить?
Okay. Well, I'm not quite sure about the teaching. The question of classifying algorithms in a kind of Mendeleev type type fashion, that's an interesting idea. I've done work on that in cellular automata, actually. I've tried to classify the behaviors of cellular automata. The classification that I made is a little bit more similar to, solids, liquids, gases type classification than it is to a Mendeleev type classification. But yes, it is a very interesting question, actually, how you can identify sort of common features of different kinds of algorithms and so on. I'm not sure about the sort of learning in a system. I mean, in a sense, in Wolfram Alpha, we're trying to we're taking data that exists in some way, and we're trying to maybe are you suggesting that what should happen is that it should look at data that exists and then try and learn from that data to deduce new data? I mean, in a kind of machine learning type way. I mean, that's certainly I mean, for something like, tides, that would be a difficult thing to do, but there are other places where it might be possible.
Алло. Такая система должна иметь единую структуру по умолчанию, раз она единая система алгоритмов. Ее нужно к этому приводить как-то, вам не кажется?
Well, okay. So one of the features of Wolfram Alpha, this is sort of a is there a single kind of ontology, a single way of representing knowledge in the system, or are there many different ways for different kinds of knowledge? The approach that we took was to just start implementing things. So we had sort of different representations of different kinds of knowledge at the beginning. Over time, we have been able to combine the frameworks to represent different kinds of knowledge using a unified framework. And it's been getting more and more unified. It's not completely unified, but it's been getting more and more unified. We have a thing we call, internally, it's called the semantic relations framework, which is our way our sort of way of uniformizing the representation of knowledge. How far we will get, I don't know. But as a practical matter, a lot of the more complicated queries that you ask in Wolfram Alpha go through the semantic relations framework. And the challenge is to kind of have the natural language, the representation of natural language, be convertible into the symbolic representation that works with this semantic relations framework. And that's sort of a trade-off. We can have very sophisticated semantics underneath, but not connect it to natural language, and then nobody can use it. We can have sophisticated natural language, but not have a representation inside, and then it doesn't work. So we have to develop both of these at the same time, and we're doing that. I think I should probably stop because unfortunately, I know you have a schedule. All right, one last question. Yeah.
Nowadays, you have the full technological stack to make researches in the area of strong general purpose artificial intelligence design, especially considering your own scientific results, for example, the cellular automation theory. Do you have such kind of ambitions?
Yes. I mean, I think, though, there's a definitional question. I mean, when the problem is, in fact, one of the things that I learned, one of the things that motivated me to build Wolfram Alpha, okay, slightly long story. When I was a kid, I was interested in kind of making knowledge computational and collecting knowledge, making it computational and so on. And I thought for many years that the only way to do that was to build a general AI, that the only way that one could actually make a large collection of human knowledge sort of computable was to do it through something that was like a brain and like an AI. What happened when I worked on the science that I worked on was I became convinced that there wasn't a sort of sharp distinction between intelligent stuff and purely computational stuff. And that was what kind of made me realize that it was worth trying to build something like Wolfram Alpha, just using computational stuff without having sort of built an AI in between. And, so the thing that's sort of a challenge now is what would we mean by an AI? We can build something that does, all of these operations that are very sophisticated, human thinking like operations. Do we want it to be something that we can have a conversation with? That's kind of the Turing idea. Do we want it to be something that, has other attributes? My guess is that we will be able to... the problem is that being able to do computations... Okay, the thing that humans have that none of these computational systems sort of can have built in is they have sort of a goal. They have goals and purposes. We can automate all kinds of things. We can do all kinds of computations. We can do all kinds of thinking-like operations. But ultimately, the question is, what does the system want to do? So we could have some box that is, a very sophisticated AI system, but it just, if it's just sitting on our desk, it doesn't, it has to be given some goal. It has to be given some purpose in order to actually, to do something definite. And that's something which, humans have for reasons of, their history and, the history of civilization and so on. They develop certain purposes, certain goals, and those purposes and goals are sort of very human things which can then be implemented either by, human brains or whatever, or potentially by computational systems. But I don't think that this idea that one can have sort of a general AI that is sort of just like a human, I think that general AI has to be even more like a human than one might imagine in order to be like a human. In other words, I think it has to have sort of human motivations and kind of human purposes and human goals and so on, and human experiences in order to actually be sort of a human-like AI. And there are certainly applications where it's useful to have systems like that. They're not quite as exciting as one might think. I mean, I think the first applications are more at the level of customer service and sort of human interaction applications rather than they are applications in the sense of, creating new knowledge and so on. This is a long... I could talk about this subject for a long time. This wasn't... But I think there's a schedule that you guys want to follow, and I know I have a schedule, so I should probably stop here. But